Alright, then welcome back everyone. Let's start with 1100 rated questions now. But before we do that, let's do some housekeeping and make sure that we all are clear with the prerequisites of this playlist. The prerequisites are as simple as it can get. You should have solved 800, 900 and 1000 rated questions, obviously. And maybe you have watched solutions from me preferably because I don't discuss solutions, right? I always discuss how to reach the solution. Like I focus more on the journey rather than the destination. The reason why I say this is because I'll use a lot of concepts and maybe the code tricks, STL tricks that I have used there without much explanation because I've already spent so much time on those videos. So yeah, so enough about that. Let's start with this question then. The question name is erase first or second letter. Now the question is pretty simple. Let me summarize it then. We are given a string s of length n and two operations are defined. So if this is string s, either you can remove the first character or you can remove the second character like this, right? The two operations are very simply defined. And what we have to output is we have to find a number of distinct non-empty strings that can be generated by applying given operations on the initial string any number of times. That is, you can take this forward as well. So this can be BC and this will be AC, right? So apply these operations any number of times and tell me how many distinct non-empty strings you can generate, and including the original string, right? Because you can possibly apply zero number of operations as well. So the input is simply the string, and output you have to give the number of distinct non-empty strings you can get. Fine. The important observation here you can see here is there are just lowercase letters, okay, and this constraints you automatically know what it means. It means that try to find a solution somewhere in n log n or less, right? Lowercase letters, whenever you see this constraints, like it helps me that to know for the fact that the map that you are going to create, if at all needed, okay, I'm not saying map will be used always, but if at all you are going to need it, you will not have its size more than 26. So all the operations, like the arrays that you will make of letters, will be bounded by this 26 letters only. So that's one thing. Lowercase letters, it means a lot of operations which you usually think consumes order of n will consume just order of 26, or in other words, just constant time operation. So this observation should be there. Fine. And how should you approach this question then? Now let's start with simple. What is the brute force here? Right? What is the brute force? The brute force would be to enumerate all the possibilities, right? So I'm just starting it simple, and let's see what is the brute force solution, and maybe we can get hint from it. How can we make it smaller? So here I've taken example ABA. So I think this is from the Codeforces only, but the answer was 9 here. Let's see how it comes. Okay, so brute force will be to enumerate all the possibilities. Let's do that. So we have ABA. Okay, so I'll just fast forward and write down all the first letter and second letter deletions because I don't want to waste your time. This is the entire tree. That is what are all the possible strings that you can generate by performing first letter and second letter deletions as many times as possible until we reach non-empty string, right? That is string of length 1. Fine. I purposefully not written here what will happen here EBA because this will be exactly similar to this. Okay, so I hope you forgive me for that. But yeah, what is observation? Like the simplest observation you can make. You should pay your attention to this ABAs, right? Because they're occurring a lot of times. How are they happening, by the way? What is happening here? How did you end up with this ABA? You first removed A, first letter deletion, and then you removed B. That is, you performed a first letter deletion followed by a first letter deletion. Fine, no issues. How did you end up with this ABA? You performed a second letter deletion followed by a first letter deletion. Effectively, you are removing first two characters, right? So, of course, this is redundant. That is, you removed a second character and then followed by first character. So, obviously, you can see you are better off taking any one of these paths, right? Removing first character 2 times is same as removing the second character and then from the first character, and it is true for any level on this tree, right? So, better off taking just one path, right? So, the first observation that you can make is removing first letter after you have just removed, after removing second letter doesn't make sense, right? It doesn't make sense, and it's not true like for just this string. You will see here. Say I'll show you for this guy. Let's say you have made a first letter deletion followed by second letter deletion, BB, right? So if you remove first letter now, you will end up with BA, right? Instead, you're better off removing the first letter from this guy, right? and you will still end up with B. Right, so this holds. If you remove a second letter, it doesn't make sense to remove first letter afterwards. In other words, if you remove the second letter, you should not take this path. You should not take this path. If you have removed second letter here, there's no point in taking this path. This is a redundant path, right? In other words, what I'm trying to say here is, once you start performing second letter deletions, you keep applying those second letter deletions, because any first letter deletion you apply is redundant. It can be achieved by more number of first letter deletions, right? Okay. What I'm saying is, once you applied this second letter deletion, don't bother applying first letter deletions, because this can be same achieved by more number of first letter deletions. That's what I'm simply trying to say. Okay, so let's simplify our tree a little bit. Okay, so here's the simplified tree. I've done nothing. What I've effectively done is, whenever I start applying a second letter deletion, I keep applying it, because I know if I apply a first letter deletion here, I could have already taken this path by applying more number of first letter deletion. So that's what I've done, right? Because I'm not taking any redundant path here. So this is the tree. And I have also taken the liberty to write the indices here, because it might give some other observation as well, right? So time for observations, round 2. What can you observe here? One thing is clear, right? If you see here at the indices, now things are getting much more clearer. Whenever you remove some number of characters, let's say you remove 1 character, or you remove 2 characters, or remove 3 characters. So I'm looking at all the string at same level, that the same number of characters have been removed. Last couple of characters are staying same. If you want to put it more concretely, if I am removing k number of characters, if I'm removing 1 character, if I'm removing 2 characters, last n minus k, so here n is what? N is 5, right? N minus k minus 1. So remaining characters would be what? N minus k. The string length would be n minus k, right? If you remove k characters, the string length would be like, here it will be 4, here it will be 3. So in this, all but the first character is same. So in other words, last n minus k, so this is the length of the string after removing k characters, every character but the first character, right? So if you observe here, apart from this, the first character at a level, if you bar this, the rest characters are same. That is, their indices are same. Here you can see 3 4 3 4 2 3 4 2 3 4. Okay, so that observation is there. So this gives you an idea when will we reach a duplicate string, right? One thing is, if you want to reach a duplicate string, the string length has to be same. That is, the same number of characters have to be removed. If you will reach a duplicate string, it will be at the same level, right? So that will be the thing, right? If you have to reach a duplicate string, it will have the same level, because same number of characters have to be removed. But now you have one more observation, that is, last characters, that is, except the first character, all the characters are same at a given level, right? So if two strings, like if there has to be a duplicate string, what does it say? So if you have two string, let's say s and s dash, these two will be same if firstly they're the same level, right? So same number of characters have to be removed, and since you know at a given level all the characters but the first character is same, this s will be equal to s dash if and only if s of 0 equals to s dash of 0, right? S dash of 0. Okay, and of course provided they are in the same level, right? That was the intuitive proof. When will you reach two same strings? If you want a more concrete proof, here, take it. Let's say we are reaching two strings, s dash and s double dash. Firstly, they will have to be at same level. Now, if you look at the nature of operations that we are doing after that optimization, that once you start applying second letter deletions, don't apply first letter deletions, because it doesn't make sense. The nature of our operations is such that you will apply some number of first letter deletion, let's say I1, followed by some number of second letter deletion. You reach any string here, there will be some first letter deletions followed by some second letter deletion, right? So any strings will have some number of first letter deletions and then some number of second letter deletion. That's what this I1 J1 and I2 J2 denotes. So this is first letter deletions, and these J1 is second letter deletions. I2 is first letter deletions for s double dash, and J2 is second letter deletions for s double dash. Fine. So how do you think this s dash and s double dash will look compared to this with respect to s? Like, what characters are present in it, right? So can you give me the indices? Let's see. So if you look at any string here, how have you reached here? You've reached by applying one first letter deletion and one second letter deletion. If you look at this string, you have come here by applying just second letter deletions. Okay, fine. So look at the first index here. Okay, it's 0. In other words, if you apply some number of first letter deletions and then start applying second letter deletion, you are not going to touch the index, like the first index that you ended up with. In other words, if you apply, let's say, just one first letter deletion, you will be here, and no matter how many second letter deletions you apply, your first character will always be this one. If you apply two first letter deletion, you'll be removing these two, and you'll be at ABA. And no matter how many second letter deletions you apply, your first character will always be 2. In other words, this S dash will start from I1, and this S double dash will start from I2, right? Because after some first letter deletions, the first character that you will end up with, let's say after first like one first letter deletion, you'll end up here. No matter how many second letter deletions you do, your first character is fixed. Fine. And what is the next character? What are the remaining characters? So what will be the remaining characters? Let's see. So let's say after performing one first letter deletion, you are here. Okay, one first letter deletion, you are here. So and then you will start applying some number of second letter deletions. So what will be the remaining indices? What are the remaining indices? It will be, in this case, I1 plus J1, right? So after removing first, like after performing one first letter deletion, you will end up with this, right? Now depending on how many second letters you remove, you will start considering indices from I1 plus J1, I1 plus J1 plus 1, right? So in other words, if you remove just one second letter, you will start from second index, right? So 0 plus 1 plus 1. So I1 plus J1 plus 1. So I guess this is very simple. I don't think I will have to dig too deep into it. So this is how S dash will look, and here it will be on the same grounds, I2 plus J2 plus 1, right? So I2 plus J2, because these many characters you will have to skip plus 1. So from afterwards you will start, right? Fine. So this is how it will look, and you know that I1 plus J1 is actually equal to I2 plus J2, because total number of deletions have to be same. So this portion is same, right? This portion is same. Okay, of course, till the end, right? Till the end, right? From I2 plus J2 plus 1 till the end, and here I1 plus J1 plus 1 till the end, like all the indices you will have. Fine. And you know that this portion is same, this portion is same, this portion is same. So if these two strings have to be same, this part has to be same. That is S of I1. Okay, S of I1 has to be equal to S of I2. In other words, the first character has to be same. Fine. So if I were to generalize, when are we gonna read the same string? Is firstly you have to apply same number of deletions, right? So let's just say we have applied five deletions. So you can either apply all the first letter deletions like this, right? 1, 2, 3, 4, 5, fine. Or maybe apply some second letter deletions, or maybe apply all the second letter deletion. Notice one thing, I'm not applying a first letter deletion after second letter deletion, because we know that that path is not worth pursuing. That's just a duplicate path, right? That we already seen. So you perform anything, but you applied first of all same number of deletion, and you are ending up at the same character. That is, the first character that you now have is same. Let's just call it A. Any which way you know that the remaining indices are going to be same. So let's just say the length of the string that you are getting after applying this many deletion is X. You know for the fact that this X minus 1 are gonna be same, right? Only the first index differ, that you already seen, right? Only the first index differs, the rest of the indices are already same, right? And also first indexes is actually going from 0 till whatever the remaining indices are, right? So here if you have 2, 3, 4, this is a 0, 1. If here is 3, 4, then it will be 0, 1, 2. That's also one thing. Fine. So that's the point. If after some number of deletions, that is same number of deletions, if you are reaching at the same character, then you will have the same string. What does it imply? Can you make some observation here? So if you look at this VA, so what I'm trying to figure out is which path should you take, right? You know for the fact that you have reached the same string, but which path is worth pursuing is my question. Or maybe you can make some other observation here. I guess one simple observation you can definitely make, that if these strings are starting with the same character, and if you keep removing the second letter again and again, you are gonna get the same string, right? In other words, what I'm saying is this path is definitely redundant, right? So in this sense, only take one of these paths. That is, once you reach the same strings, all the second letter deletions going forward will also repeat, right? So you are better off taking just one of the second letter deletions path, right? Again, if you see here BA, all the second letter deletion, okay, there is just one. All the second letter deletion, there is just one, fine, but it will be redundant. If you want to give you a more general example, let's say you have A followed by some letters, here. If you keep on applying second letter deletions, the first this will go, then this will go, this will go, this will go. This is the same path, right? So this two paths will be exactly same. So better off just taking one path. So that's one good observation, that if you have reached two same strings, second letter deletions going forward are gonna be same as well. In other words, what you have just seen is if s dash equals to s double dash, then all the second letter deletions will lead to the same string. That's obvious, right? Because the first character is same. If you keep on deleting second letter, it's still gonna lead to the same string. Okay. This is one observation. What else? What else can you see? Another thing you can easily see here is, let's say after some number of deletion, like same number of deletions, you are reaching A. Okay, you are reaching A here, and there will be last couple of indices left. So I don't really care what these indices are because they are gonna be same. So let's just, for brevity, let's say this is some 99, 100, 101, something. Doesn't really matter to me at this point what these indices are, but they are gonna be same is what I care. So apparently this string is going till 101th index. What can you say about these A's? Like, of course, they will also have some indices, right? So how are we performing deletions? The deletions we performed are of form like this, right? So first letter, then if we start applying a second letter deletion, we always apply second letter deletions, right? So that's how we are doing, because we know that after we have started applying second letter deletion, it doesn't make sense to apply first letter deletion. So that's a very important point. Okay, all right, come back to this example. So you know that this last couple of characters are same, fine. Then what can you say about these three A's? Okay, so this three A's definitely will lie somewhere here, right? It will lie somewhere from 0 to 98, right? Your A's will be somewhere here. I don't know, let's say without loss of generality, these are the A's that you have, let's say at index 9, 20, and some 30. Okay, so all in all, what I'm trying to say here is you will have a A here in this part with its lowest possible index, that is the index of the first occurrence of A, right? So A might be somewhere here at the 9th index, then at the 20th index, and then at some 30th index. That's what I'm trying to say. It is definitely right. So how can you reach this A? Of course, keep applying first letter deletion until you reach the 9th index, right? And this remaining index, how can you reach this 99? Keep on applying the second letter deletions afterwards till you reach the 99th index, right? Similarly, keep applying first letter deletions till you reach the 20th index, and then keep applying the second letter deletion till you reach the 99th guy. Same, on the same grounds, keep applying first letter deletions till you reach the 30th, and then keep applying second letter deletions till you reach 99 in the second position. Pretty simple here, right? My argument to you here is, if after some first letter deletions, you are reaching a letter which is not its first occurrence, right? Here, if you are reaching this A which is not its first occurrence, this path doesn't make sense to us. Why? Because this same thing can be achieved by a guy with its lower occurrence. Okay, again, to reach this A, you would have applied some first letter deletion. To reach this A, you have applied some first letter deletions. To reach this A, you would have applied some first letter deletions. My question is, if you are reaching this A at the 30th guy, and it is not its first occurrence, this path doesn't make sense to you. Why? Because the same thing can be achieved by less number of first letter deletions, right? So you can delete less number of first letter to reach the same A, followed by some number of second letter deletion, right? So you can perform less number of first letter deletions followed by some more number of second letter deletions to reach this same string, right? So this is a very important observation. If after some number of first letter deletions, you are reaching a character which is not its first occurrence, this path is better not taken. That is, this path is already taken when you apply some less number of first letter deletions and you reach the first occurrence of that same letter followed by some second letter deletion, right? So definitely second letter deletions for this guy will be more than this guy, but there's no point in taking this path. This path can already be taken. All in all, what it proves is from the first occurrence of a letter, right? From the first occurrence of a letter in the string, all the second letter deletion going forward yield a different string, right? You just don't need to consider other occurrences of this letter, right? So from the first occurrence of a letter, all the second letter deletions going forward yield a different string, right? From the first occurrence of a letter, all the second letter deletions yield a different string. Now here, if you know, there can be only maximum 26 unique characters in your string, right? Because it is given, your string only contains lowercase letters. All in all, what it proves is, from all the unique characters, all the unique characters that you have, all the unique characters in S, all the unique characters in S, all the second letter deletions going forward yield a different string, right? And you know that can be maximum 26 characters. And what if you want to find out how many of those unique second letter deletions are? It's obvious it will be some index logic, right? So more specifically, so from this guy, let's just take this example only. From A, all the second letter deletions going forward yield the unique string, or maybe no deletion, right? All the second letter deletions or maybe no deletion. So this is one string, then this is one string, this is one string, this is one string, and this is one string. So this can be, I guess, achieved by what? This is n minus, what is the first occurrence? It is, let's call it I. So n minus I. So 5 minus 0, right? 5 minus 0. How many strings are there? If you want to count, it is 1, 2, 3, 4, 5. Right. So from a first occurrence of a letter, all the unique second letter deletions are n minus I. So if you want to see one more example, let's see. The first occurrence of B, how many second letter deletions are there? 1, 2, 3, 4. So it is again n minus I only, right? N minus 1 only. 5 minus 1, 4. So that's that, right? So all in all, what it says is, from all the unique character in S, find out how many second letter deletions are possible, and this will give you unique strings. Now my question is, can you see that this is an exhaustive enumeration? In the sense, this covers all the possible unique strings that you can generate. Can you see it? So what I'm trying to say here is, from all the unique characters in S, find out how many second letter deletions are possible from its first occurrence, and that you can maybe add to a total count. So total can be plus equals to n minus the first occurrence, right? So n minus first occurrence of this character, right? So this will be it. But my question is, can you see that this is exhaustive list? You are covering all the possible string. If you can see it, then this question is done and dusted. Otherwise, wait for it. I'll give you a quick 2-3 minute summary of what we've achieved till this, and why this actually is exhaustive enumeration. Okay guys, so let's just complete the question now. So let me first give you a summary of what we discussed till now, because I guess the video has already become so long, but I think it was worth it. So we started with the brute force way of enumerating all the possible string. Then we figured out that once we have made a second letter deletion, first letter deletions going forward is redundant. This path is already taken by consecutive first letter deletions, right? Then we figured out if two strings have to be equal. First of all, same number of deletions have to happen. That is, they should be at the same level of the tree that we have drawn, and the first character has to be seen, right? Moreover, if you have figured out that two strings s and s dash, s dash and s double dash are equal, then second letter deletions going forward will be redundant. That is, you are better off taking just one path. Not only that, we also find out that since the first character is same in all the strings that are same at a given level, we are better off just considering the letter with the least possible occurrence. From that, we got a very important observation that second letter deletions from the first occurrence of a letter always yield a unique string, right? In other words, if you can just collect all the possible second letter deletions from unique characters in your string, then your job is done. Now, if you cannot see this, let me give you an example. Let's say our string is starting from A. Okay. Now you know for the fact that all the second letter deletions here are gonna yield a unique string. So this path is fine. So and this value will be actually n minus the first occurrence index of A, right? So these many strings will be unique that you can form. Now what happens after you make a first letter deletion? If you receive A here, then there is no point in taking the second letter deletion path. This is duplicated, right? Because these all strings you can receive here, right? The less number of first letter deletions to reach this guy, right? Zero number of first letter deletions to reach this guy, followed by some second letter deletions, will give you all the possible strings that you can achieve in this path. So this path is redundant. I'll highlight it probably. This path is redundant. There's no point in taking this path. Fine. So second letter deletions are redundant. What about first letter deletion? Now, after first letter deletion, like 2 times first letter deletion, if you're again reaching A, Again, on the same grounds, all the second letter deletions here are redundant. There is no point in taking this path because they can be achieved by less number of first letter deletion to reach the first occurrence of A and then doing second letter deletions depending on the string that you want. Fine. So let's move forward then. Let's say after first letter deletion, so this was about second letter deletions. What will happen for first letter deletion? Let's say you get B. From B, you can do second letter deletions. They all are gonna give you a unique possible string. Fine. So that's fine. And what about the first letter deletion? For the first letter deletion, if you receive B, on the same grounds, all the strings that you are gonna achieve here in the second letter deletions, you can achieve by less number of first letter deletions, reaching the first occurrence of B and performing second letter deletions. That is, this path is also redundant. There's no need to take this path because all the strings on this path can be achieved by less number of first letter deletions and reaching the first occurrence of B followed by second letter deletions according to your need, the string that you want to generate. Fine. So let's move ahead then. For the first occurrence, if you receive A, second letter deletion path is not required, right? This path is not required. Then what happens if you get, let's say, C, right? If you get B here, then again second letter deletion path, this is redundant, right? Because the same can be achieved by less number of first letter deletions and reaching the first occurrence of B followed by some second letter deletions, right? I guess you are getting it. So for example, if after applying first letter deletion you can get C here, all the second letter deletions will give a unique string and so on, right? Let's say this is where the string ends. So this thing, I guess you can take it from here that to enumerate all the possible unique strings in this S, when you have only two operations available, either first letter deletion or second letter deletions, you just have to enumerate all the possible unique second letter deletions, right? All the possible unique second letter deletions, right? So I guess this proves it. And the code is very simple actually, so I don't think I'll show you, like, write the code in front of you. You just have to find out first of all how many unique characters are there and note down its first occurrence. So this is a very simple thing, right? So this, I guess you already know how to do it. We are just finding out the first occurrence of every unique character, right? We are just finding out first occurrence of every unique character in S, right? So this is a simple loop, and then I'm just adding the individual unique string counts from a letter to the total. In other words, what you are effectively doing is you are finding out number of unique strings starting from each possible character. So for example, if you have, let's say, 3 unique characters in a string ABC, what effectively this thing is doing is it is enumerating all the possible unique strings starting with A, starting with B, starting with C, right? That's what you're doing. So yeah, I mean, that's that about this question. And what is the time complexity? So time complexity, this will be what? This will be a order of n loop because you are enumerating the entire string, and this will be maximum order of 26 loop. So the total time complexity is just order of n, right? So yeah, that's that, and this very well fits in the constraint. So I hope you got something out of this video. I'll see you in the next one then.